So spectrophotometry is an extremely useful tool to measure concentrations, as you've probably experienced in the practical. And it is really based on how electromagnetic waves interact with matter. And once you've understood that and got the concept, then you can see what we can do with that. So here is a picture of the electromagnetic spectrum, and it contains visible light. So that's basically, no, that's the wrong one, sorry. I want this one. So that's basically what we can see, or the light, the electromagnetic waves that we can actually observe by eye. And these electromagnetic waves are usually expressed in a certain wavelength. Let's not worry too much exactly how this wavelength is measured, but it suffices to say that blue light is in the range of 400 nanometers, whereas red light, what we see as red light, is in the range of 700 to 800 nanometers. And electromagnetic waves, well, they can range from very, very long waves. These would be radio waves, for example, here. These would be gamma rays here, as we see in some supernova explosions. Here are X-rays that occur when atoms disintegrate, and so on and so forth. So there is a huge spectrum. In biology, usually, we are not too worried about this range here, about radar and radio waves. And we're usually not too worried about gamma rays, although there are also applications for gamma rays. Now, a very specific thing about all these electromagnetic waves is that they have the potential to interact with matter. And they interact in a specific way. So what happens when there is an electromagnetic wave, and I symbolize it like that. So that's a sort of a wave coming along. We know, for example, that light can be either just this energy thing, or it can be a little particle, but again, that's not something we need to worry about too much. So what happens if this wave hits matter? Let's say something like that. In this case, molecules within this material will catch this energy. So they will take up this energy. But there's a slight complication. Not all materials will be suitable to accept this. And this is because all materials are, of course, made of atoms. So here is the nucleus of an atom, and here are the electrons whizzing around. And you've seen that in chemistry. So they are floating around. Now these electrons are really particular. They are running only on certain orbits, if you like. It's not entirely true. It's not orbits. It's sort of more. It's a sort of a cloud thing. But for the time being, let's say it's sort of orbits, like planet orbit the sun. And electrons can only do that for very particular orbits. So, for example, this orbit here has 2 electrons. And these electrons have a very defined path. They have a very defined energy, in a way. They can only run on this orbit. So if I give them extra energy, give them a kick, what happens is the electron has 2 options. The electron can then, if it gets this kick, if it's a, let's say here is the electron orbit, if I look at it from the side, if I give it this kick with this light energy, if it is exactly the right energy, I can kick it up to the next level. So the electron could jump up here. And just to illustrate that, Johannes, can I quickly borrow you, please? Right, now here is the electron, right? And he is perfectly happy here on this level. Now I am the light, and no. Was that really that bad?
No.
No. Yeah. You see, I don't have the right energy to move him up the next level. Turn around. Let's see if I get the right energy to kick him up, only one. Yeah, okay, fantastic. Yeah? In this case, he can move a little bit, he has a little bit of leeway, but usually electrons don't have that. They can either go up here when the energy is exactly right or not. If the energy is not right, if it is too high or too low, the electron says, sorry, master, no can do. Thank you very much. Yeah? So the energy has to be exactly right. Now, if I have different energies, and I symbolize it like that, if I have different energies, there is certainly one energy that is right to move the electron. But what would happen if my energies of the light are all the same? Then it has to be exactly the right energy for the electron to move it up, otherwise it wouldn't move. This is how matter, how atoms actually interact with electromagnetic wavelengths. Now I want to give you another little experiment. And can I quickly borrow you? Thank you. I just have to say, it might hurt a little bit.
Okay.
Yeah? Are you okay for that?
Yeah.
Okay, fantastic. Now, can you please stand here for a moment here? Yeah? Face this one here? Yeah? Okay, good. Let's see. Now, what's happening now is my iPad is sending a Wi-Fi signal over to this Apple TV, and that is how I can, move things around. So you see the signal works. Now let's see if I can zap him. Yeah? Does this still work? Does this work? Oh yes, it does work. So I'm sending energy in form of Wi-Fi signal, of wave, electromagnetic waves, over there. But it's going through him. Does it hurt?
No, but a little bit.
A little bit, yeah. Yeah, I know, but that is probably because it's morning. Thank you very much. Why didn't it really hurt him? Why didn't it hurt him? It didn't interact with him. The wavelengths, the energy of the Wi-Fi did not interact with him. Because his electrons in his body are not absorbing this energy. They are just simply not in the right mood, on the right energy levels. Yeah? Now you have done all very similar things. Most of you have done that because you have used, for example, a microwave. Okay? I doubt that there's anyone here who has never used a microwave. How does a microwave oven work? How does a microwave oven work? How would you explain that to somebody who has never seen a microwave? No? Loud? What does it do? If you put some food in the microwave, you put the microwave on, why does it get hot?
Do the water molecules vibrate?
Yes, exactly. What happens is that the microwave oven sends out electromagnetic waves. And these waves have exactly the right energy to be absorbed by the water molecules in your food. Now, usually molecules are moving a little bit around, yeah, like that, moving a little bit around. But now they are getting more energy. You can see what happens. They are starting to get really agitated, yeah, these poor little molecules, and I'm getting really hot now, yeah, and so does the water molecules. They just bounce around now because they absorb all the energy. And that is why your food gets hot. What would happen if you just put an empty plate in a microwave and turn it on? Nothing. Does it get hot? Why not? There's no water in it, usually in the plate. Yeah? There's usually no water in the plate, so it doesn't have the right molecules, and these molecules don't absorb the light. Does that make sense? At least it does to me. So, materials absorb light, but it has to be, or electromagnetic waves, but it has to be exactly the right wavelength, the right energy in the light. Otherwise, they wouldn't absorb it. That's also the reason why we see different colors. Let me just quickly do something. So here's the question. Why are leaves green? Why are leaves green? Smell? What is it? Any biologists here? Are you a biologist? Sorry. No? Very characteristic smell? Rosemary, yes, exactly. This was the only one that I could find, which I quite like. So why are leaves green, please? The chlorophyll, okay. What does the chlorophyll do apart from photosynthesis? Why does it make the leaves green? Sorry?
Absorbs the green wavelength.
It absorbs the green wavelengths.
Doesn't it absorb everything else but green? Sorry.
Wait a moment. Okay, correction. Say again.
It absorbs everything but the green.
It absorbs everything but the green. Exactly. It absorbs light in the red wavelength, and it absorbs light in the blue wavelength range. So what's left is a greenish color. Yeah? Make sense? Why do the leaves turn red in autumn? Indian summer. Why do they turn red? Any ideas? Sorry? It's less chlorophyll. Exactly. Chlorophyll is a very precious molecule, and the plant is trying to recycle the chlorophyll. So it degrades the chlorophyll. And therefore, there is no absorbance any longer in the red and in the blue range. Instead, there are other plant pigments in the leaf that you usually don't see, because they are just covered by the chlorophyll. And these plant pigments usually absorb in the red and green and yellow range. But they don't absorb in the... Sorry, I said complete bollocks here. It is blue and yellow range and green. But they don't absorb in the red range. So that's why we see these colors as red. Yeah? Makes sense? So, how does this now actually... Oh, by the way, you can do a really, really nifty experiment with a microwave. I don't know whether you've done that in physics, but you can actually measure the speed of light with a microwave oven and a Mars bar. Mars bar and a microwave oven. If you're interested in that, I will post the way how you do it. And it's pretty accurate, actually. It's absolutely amazing how you can do that. So if you are planning to become a physics teacher, that's definitely a really cool experiment that you can show your kids. Anyway, how does that figure with what we've done on Tuesday? Well, let's do a little experiment again. Let's say we have a container and there are molecules in it. Like this, and this. So I see this as orange. I don't know. My wife says I have no sense of colors. That's why I end up with, a blue and a black sock usually, because I can't see colors very well. But these are orange molecules, let's say. And we see them as orange because they absorb anything but orange. It's a little bit like me. I'm on a grapefruit diet. I can eat anything but grapefruits. Right? So with absorbance, it's a similar thing. So let's say I shoot light through, and this light is absorbed by particles. Bless you. What happens to this light? let's say I have 1, 2, 3, 4, 5 of these. What would you think will happen when I shoot a certain amount of light through this solution? In terms of if these particles absorb the light, if it's the right energy, will I get the same amount, five wavy things, will I get this out at the other end? No. Why not? I get far less out. Yeah? Let's say I just get 3 out. So what we say is the particles absorb, and what goes through, the transmission, goes down. Yeah, does that make sense? Transmission is how much goes through. Yeah? What would happen if I add more particles? And still shoot the same amount of waves through? What would happen? Less goes through. Maybe now only one goes through. Yeah? So, in a way, the transmission of the light that goes through depends on the amount of particle. So, transmission depends on amount of particles in my container, in given volume. Yeah? The more of the particles I have, the less goes through. Or I can turn it round and say, the more particles in this container I have, the more energy of the light is absorbed. Yeah? So the absorbance of the light goes up depending on the amount of particles. I can say absorbance increases with amount of molecules in the volume, in the given container. Wait a moment. We said amount per volume. What do we call that? Amount per volume. What is that? It's a concentration. So what we can actually say is absorbance, and I just simply call it A, is proportional to the concentration of my substance. Does that make sense? Yeah? Absorbance is proportional, that's this wavy thing, is proportional to the concentration. Okay, great. I buy that. Now, let's do something funny again. Let's take a few of these things out. But instead, so let's say there are now 2 going through. 2 of the waves are going through. I'll reduce the concentration so more goes through and less is absorbed. But now I make this container bigger. I make this container twice the size. Of course, I have to add more of my stuff here, yeah, so that it has the same concentration. So that was the old container here, but now I doubled it. What would happen to the transmission? More or less? It's less, isn't it? So when first 2 went through, now maybe only 1 goes through. Yeah? So the transmission depends also on how big the container is, how long the container is, or the absorbance. The absorbance also depends on the length that the light has to go through the container. Long container, more gets absorbed. Small container, less gets absorbed. So absorbance depends on the path length. So our absorbance really depends on the concentration of the substance and the path length. Wouldn't it be nice to combine this into a nice thing that we can deal with? Actually, we can do that. We can write absorbance equals the concentration of the substance times the path length times a factor that converts these proportional to an equal sign. And we just simply call this thing, what do you want to call it, this factor? Henry? Hugo? Matilda? Well, actually, the chemists call that an extinction factor. Yeah? And because chemists hate to write out these things, they write it as A, absorbance, or sometimes they also call it E for extinction. Absorbance and extinction are the same things. Not in genetics, mind you. Extinction is a different thing then. You know, you can't say that the dinosaurs were absorbed. They got extinct, but it's a different thing. Absorbance or extinction equals C, that's the concentration, times D, that's the path length, times the extinction coefficient or extinction factor, which is an epsilon. It's sort of like a 3 that is doing yoga. Okay? Now this is actually a very, very important equation. And because it's so important, it has a name. Any idea what it's called? It's called the Beer-Lambert law. Beer-Lambert law. apparently two people, one called Beer and the other one Lambert. I mean, I hope I don't upset anyone here, but if you have a surname called Beer, hey, that's a fantastic chat-up line, isn't it? Yeah? Fancy a beer? Now, this is an absolutely crucial equation that you must learn and must be able to apply. And if I phone you on Sunday morning, 2 o'clock, and I say, what is the Beer-Lambert law? You have to tell me absorbance equals concentration times path length times the extinction factor. And then I'm a very happy person. Not that I'm going to phone you at 2 o'clock in the morning, because I usually sleep at that time, but, you know, it could happen. Absolutely important. So what can we do with that? We can measure the concentration of a substance. We put the substance into one of these little cuvettes that you've used. Yeah? Then we shoot light at exactly the right wavelength through. It has to be the right wavelength, because otherwise these molecules won't interact with it. And we measure what's coming out at the other end. And from this absorbance here, we can calculate the concentration if we know the extinction factor. Yeah? And people have determined extinction factors, so you can usually look up these extinction factors in handbooks and things like that. So let me give you a little example. Let's say we measure an absorbance of 0.2. That's our absorbance. The extinction factor equals let's say 1 molar to the power of 1 centimeter, and we come back to the units in a minute. And we do that in a 1 centimeter cuvette. And you used a 1 centimeter cuvette where this path length was just 1 centimeter. So D equals 1 centimeter. Yeah. I forgot that. Okay, so what is the concentration? So we have A equals C times D times epsilon. We can very easily rearrange this equation and get C equals A divided by D times epsilon equals 0.2 divided by 1 times 1, and that gives us a concentration of 0.2. Now, obviously, we need to discuss the units. So, let me rewrite this again. Concentration, so A equals C times D times epsilon. Concentration we measure in mole per liter. Yeah? The path length, the d, is usually a 1 centimeter, but you can also get different cuvettes, 2 centimeters, 3 centimeters. You can get even very, very, very small cuvettes. 1 microliter, or 1 microcentimeter, 1 micrometer, 1 millimeter. Very small cuvettes. So you need to bear that in mind. So 1 centimeter. Now, what is the unit for this epsilon? The absorbance has no unit. Yeah? Absorbance has no unit. Can we figure out what this epsilon has? Well, what we can do is we can treat that like an equation. So we bring everything to that side, and we get we get liter over mole times centimeter. That is the unit for epsilon. Or we can write it as molar to the power of -1 times centimeter to the power of -1. That's the unit of this epsilon. Yeah? Right. Now, this epsilon, the epsilon itself, depends on the wavelength. So epsilon depends on the wavelength of the light. And different light energies have different epsilons. So you always have to say at which wavelength you measured or you have this epsilon. So for example, we did the experiment at 405 nanometers, yeah, for the paranitrophenol, and in this case the epsilon would be at 405. So you need to specify at which wavelength you are looking at the whole thing. So epsilon depends on the wavelength. A equals C times D times epsilon. This is the Beer-Lambert law again. Does this directly depend on the wavelength? Is there a wavelength in it? Directly. Is there a wavelength in it? In this equation? No. There isn't a wavelength in it. The wavelength is only in this epsilon. Yeah? But not in the Beer-Lambert law. Many third-year students say, oh, I remember, you have to calculate, wasn't there something with a wavelength? Yeah. I just multiplied by 405. There's no wavelength in it. So don't multiply with wavelength. Just A equals C times D times E, epsilon. C, D, E. A, B, C, D, E. It's fairly easy to remember, isn't it? Right. Now what you can do is, if you don't know the epsilon, you can do something really, really funny. What you do is, you take your substance, and you shine lights through it and see at which wavelength the substance absorbs. So, like I showed you with Ioannis earlier, if the energy is not right, there is no absorbance. So with blue light, for example, there's no absorbance. The stuff doesn't react. If I then, so at a certain wavelength, no absorbance. If I then use other light, I see that there is absorbance. If I use light of yet another wavelength, there's more absorbance, or less. So what I can do is I can do a plot. I can say, here I measure my absorbance, and here I measure the wavelength of the light. That would be in nanometer. What's the unit for absorbance? Loud? There is no unit. Exactly. Wonderful. Thank you. So what you could see is something like that. So this particular substance has a very high absorbance at this particular wavelength here. This is actually called a spectrum, because I use a wide spectrum of wavelengths. Different substances have different spectra. This would be actually here, this would be an absorbance or absorption spectrum. It just tells us at which wavelength this substance absorbs best. And the really clever thing is, you can use these spectra actually to identify substances. You can look up in a catalog what happens if my substance that I have has a very high absorbance, let's say at 280 nanometers. This is in the UV range. We wouldn't see that any longer, but it's a perfectly acceptable wavelength. If this substance has an absorbance, a very high absorbance at 280 nanometers, this is usually an indication for nucleic acid. So it could be a DNA or RNA. If it has an absorbance at 220 nanometers, it's a protein. We don't know which protein, but we know it is quite likely a protein. Does it make sense? Yeah? So you can use these spectra to identify substances. And then, once you know what substance it is, or if you know what substance it is, you can also then measure the concentration of this thing. Just with, you get 2 for the price of 1. Isn't that clever? Now, sometimes we don't know exactly the extinction coefficient. This is because the extinction coefficient could vary very easily depending on the conditions, and we will discuss that in one of the next lectures, how the environment can affect molecules. So what we do is, if we still want to calculate our concentration, what we can do is we can measure known concentrations of a substance. So measure known concentrations and see what is the absorbance. what is absorbance. So what we do is we prepare samples with different concentrations where we know the concentration, and we plot. So here, for example, I've got a concentration of 1, 2, 3 milligram per milliliter. That's a concentration. Yeah? I can use that as a concentration, or millimolar. And I find my absorbance is something like that, 0.1, 0.2, 0.3. And what I get is something like that. Yeah? Hopefully a straight line. Because the absorbance is directly proportional to my concentration of the substance. So I get a straight line. This is actually called a standard curve. Standard curve. Curve, a line is a curve, you know, it's just a straight curve. So it's a standard curve. And now, what I can do is I can measure an unknown concentration. Let me do that in red. Unknown concentration. And I find, for example, this unknown concentration has an absorbance of 0.2. So this is the unknown, the red one. Can I find out what is the concentration of this unknown? Can I? Absolutely, because I know that in my standard curve, a concentration of 2 milligram per milliliter gave me an absorbance of 0.2. My unknown concentration also gives me 0.2. So I know that my unknown concentration also is 2 milligram per milliliter. That's where this beauty where it gets really nice with these standard curves. Because the standard curve gives me sort of a map. Does that make sense? Yeah? Okay, now, last thing for today. Here is my standard curve. Absorbance. And here's my concentration. And I've got that. Okay? That is my standard curve. And now I measure my unknown concentration. And I get for my unknown absorbance, unknown absorbance equals 0.45. Okay? That's what I get. What is, I should say milligram per milliliter here as a concentration. What is actually my concentration of this? Can I do that? No? Why not? Why can't I do that? Why can't I?
It's outside your data range.
It is outside the data range. Thank you very much. What that means is my absorbance would be here. I would need to interpolate and hope for the best that it hits they are hitting here. Yeah? That is what a lot of people do wrong. And then they say, oh, well, it's up there. I just simply extend the standard line and do that. But what would happen if your standard line, you couldn't extend it? If your standard line actually did something like that? You don't know, because you haven't measured in that range. So never ever use a standard line to extrapolate data. You can only measure data for which are within your measured range. Yeah? Never outside. This would be abuse of a standard line. Does that make sense? Any questions? I've put up some videos and a little self-test. You can do the self-test at your leisure. I'm not setting any deadlines for that, but do it and see whether you can use it, because this would be an assessed practical in week 8. I shall see you tomorrow for the post-lab. There will be attendance sheets.